Hey everyone, welcome back to The Explainer. If you're a focused learner ready to conquer the sometimes tricky world of thermal physics, you have landed in the perfect spot. Today, we're taking a deep dive into thermal properties and temperature. But don't worry, we aren't just going to sit here and read dry textbook definitions. Instead, we're going to break down real rigorous test questions step by step to really sharpen our logic. We'll figure out exactly how materials absorb heat, what actually happens when they melt, and the brilliant science behind how we measure the whole shebang. All right, here's our roadmap for today. We're hitting the thermal sponge effect, doing a step-by-step on heat capacity, checking out the plateau of phase change, breaking down latent heat, and finally looking at the science of thermometers. Let's get right into it. Section 1. The thermal sponge effect. Understanding heat. So, specific heat capacity. Forget the formal definition for a second. Think of a material's heat capacity as a thermal sponge, right? A substance with a really high specific heat capacity is basically a giant, super absorbent sponge for heat. It can soak up a massive amount of energy before its own temperature actually starts to rise. Picture yourself at the beach on a totally scorching summer day. The sun is just blasting both the sand and the ocean. The sand, it gets so incredibly hot it's literally burning your feet. But the ocean water feels amazing and cool. Why is that? Because water has a massive specific heat capacity. It just takes way more energy to heat it up compared to that dry sand. We see this exact same thing with metals in our source materials physics problems. Let's look at copper and lead. Copper actually has a significantly lower thermal capacity than lead. So what happens if we blast identical blocks of both metals with the exact same amount of thermal energy? Well, because copper has a much smaller thermal sponge, it fills up almost instantly. Its temperature is going to spike way higher, way faster than the lead. It simply cannot hide that thermal energy. Moving on to Section 2, step-by-step heat capacity, doing the math. Okay, let's put this thermal sponge idea to the test with some actual math. Here's a direct challenge straight from the source paper. Imagine we've got a beaker containing 0.5 kilograms of water, sitting at a pretty chilly 3.0 degrees Celsius. We heat it up, pumping an extra 21.0 kilojoules of energy into that water. We know water's specific heat capacity is 4,200 joules per kilogram degree Celsius, so what is our final temperature going to be? Now, the trick here is to never rush the math. Let's break down the logic step by step. Step 1, we gotta get our units to match. 21.0 kilojoules is 21,000 joules. Our mass, M, is 0.5, and our heat capacity, C, is 4,200. Step 2, we grab our classic thermal energy formula, E equals mc delta T. We need to find that temperature change, the delta T. So we divide 21,000 by the product of our mass and our capacity. 0.5 times 4,200 is 2,100, and 21,000 divided by 2,100, that's exactly 10. So our temperature jumps by exactly 10 degrees. But wait, step 3, we are not quite done. We have to add that change back to our starting temp. Remember, we started at 3.0 degrees Celsius. Add that calculated 10-degree bump, and we land perfectly at our final answer, 13.0 degrees Celsius. See? Step-by-step logic wins every single time. Section 3. The plateau of phase change, breaking bonds. All right, so normally adding heat means things get hotter. We just proved that. But physics absolutely loves throwing us a curveball. Enter latent heat. This is the energy involved when a substance actually changes physical state, like a solid block of ice melting into a puddle of water. And here is the wildly counterintuitive part. During that exact moment of phase change, you can pump enormous amounts of heat into it, and the temperature, it won't budge, not even a fraction of a degree. It stays completely, entirely constant. Just take a look at this heating curve graph. We're continuously warming up a solid. See that steep climb from P to Q? That's our specific heat doing its thing, warming the solid up. But look super closely between points Q and R. We are absolutely still adding heat, but the temperature line goes totally, perfectly flat. It's a plateau. What's happening here? Well, the substance is busy melting. It's partly solid, partly liquid. All that incoming thermal energy isn't making the molecules vibrate faster anymore. Instead, it's literally being consumed by the heavy lifting of ripping those molecular bonds apart to melt the solid. And you know, this is a two-way street. When a solid melts, it's devouring energy from its surroundings, but staying at that perfectly constant temperature until it is 100% liquid. On the flip side, when a liquid freezes or solidifies back into a solid, it's actually releasing thermal energy out into the world. But again, that temperature stubbornly refuses to drop any further until the entire freezing process is totally finished. Section 4. Step by step, latent heat, combining concepts. Okay, let's level up. We're going to take everything we just learned and mash it together in one big dynamic scenario. Imagine 5.0 grams of warm water at 25 degrees Celsius. It drips right onto a massive block of ice that is sitting exactly at its melting point of 0 degrees. The warm water cools all the way down to 0, and obviously some of that ice is going to melt. Assuming a perfectly efficient energy transfer, we need to figure out exactly how much ice melted. We're given water's specific heat capacity at 4.2, and the latent heat of fusion for the ice is 340 joules per gram. Let's walk through the logic step by step. Remember, energy can't just disappear. The exact amount of energy our warm water loses has to equal the energy the ice absorbs to melt. It's a one-to-one trade. Step 1, let's find that lost energy. Using E equals mc delta T, we multiply 5.0 grams times 4.2 times that 25-degree temperature drop. That equals exactly 525 joules of thermal energy released. Step 2, connect the dots. The ice gets that exact 525 joules. Step 3, apply our latent heat formula. Mass equals energy divided by latent heat. So we just take our 525 joules and divide it by 340. Crunch those numbers, and 525 divided by 340 gives you roughly 1.54. Check the options from our source problem, and boom, our correct answer is 1.5 grams of melted ice. What looks like a crazy complicated interaction actually becomes super straightforward when you track the energy step by step. Section 5. The science of thermometers, measuring reality. Let's take a quick break from the math and look at the actual physical hardware we rely on to measure all this stuff. The classic liquid-in-glass thermometer. It looks incredibly simple, right? But it's pure applied physics. It works entirely on a principle called thermal expansion. As the liquid inside the glass bulb, usually dyed alcohol these days, gets hotter, it expands. Its volume increases. And since it is completely trapped inside that glass bulb, it has absolutely nowhere to go but up that incredibly tiny, narrow stem, pushing the thread of liquid further along the scale. But what if we need to measure super tiny, minute shifts in temperature? How do we make the thermometer sensitive enough that the liquid actually moves a noticeable amount? Physics gives us two really cool mechanical design tweaks for this. First, you could just make the glass bulb bigger. Holding more liquid means a greater overall volume expansion for the same exact temperature change. Or, alternatively, you could decrease the internal diameter of the tube itself. If you force that same expanding liquid into a much tighter, narrower tunnel, it literally has to travel further up the glass stem. Both of these tweaks make for a far more sensitive instrument. Of course, a sensitive thermometer is totally useless if it isn't accurate. So imagine you build a completely blank thermometer from scratch. How do you actually know where to draw the lines on it? You calibrate it using fixed points, constants of nature. Step 1. You shove the bulb into pure melting ice. Remember our plateau of phase change? The temperature is totally locked in. Wherever that liquid stops moving, you scratch a line and call it 0 degrees Celsius. Step 2. Plunge it into pure boiling water. Another stable phase change. Mark that spot as 100 degrees. Step 3. As long as that liquid expands uniformly, you can just confidently chop up the space between those two marks into 100 perfect little degrees. Let's wrap this up with one last rapid-fire logic puzzle based entirely on that idea of uniform expansion. Imagine our totally blank, uncalibrated thermometer has a liquid thread that's exactly 2.0 centimeters long when it's plunged in 0-degree water. Put it in 100-degree water and it stretches all the way out to 26.0 centimeters. So here is the question. Exactly how long is that thread when the water is exactly 50 degrees Celsius? Just think about the geometry here. 50 degrees is dead center, right? Exactly halfway between 0 and 100. And since the liquid expands evenly, the length has to be exactly halfway between 2.0 and 26.0. The total gap there is 24 centimeters. Half of 24 is 12. Add that 12 back to our starting point of 2.0, and you perfectly hit 14.0 centimeters. Nailed it. Wrapping things up today, I want to loop back to a question posed right at the start of our source material. The same quantity of thermal energy is given to two objects. What accounts for this difference? Hopefully, this entire explainer has proven to you that heat is not just some generic one-size-fits-all force. It interacts uniquely with the highly specific physical architecture, the thermal capacity, the mass, those latent bonds of absolutely every single material it touches. We've spent our time today seeing how heat alters temperatures and forces phase changes. But I really want to leave you with this provocative thought. If heat is really just invisible energy at work, dictating everything from the tiny expansion of alcohol in a glass tube to the melting of massive blocks of ice, how else is it secretly shaping the colossal architecture of the physical world around us, way beyond just making things hotter or colder? Think about that the next time you feel the sun on your back or watch a pot of water boil. Thanks so much for diving deep with me today, and keep asking great questions.